Okay, so since we have a bit of time, we're a little bit ahead on a few topics, and I was getting way too many blank stares when I was asking about heaps. I was going to go ahead and do a quick review of heaps, and then we'll do a review of binary search trees. Both of these are going to be motivators for our real topic, which is going to be balanced binary search trees. So just as a review here, remember that heaps are they're tree-based data structures. And a heap is a binary tree, so every node has at most 2 children. It could still have 0 children and be a leaf. It could still have 1 child but not the other child. But it also has these additional properties. It's not a binary search tree, first of all, because every node has a key that is smaller than both of its children. This is called a min heap. If you flip this around and put in larger than both of its children, then you've got something called a max heap. But it's also full. All nodes are present at every level except possibly the last level, that is the deepest level. And even then, at the last level, it is full to the left. So in other words, it's a highly packed tree, a highly packed binary tree. Not binary search tree, but binary tree. Let's look at a really quick example and start to glean some properties at this, of this. So again, it's a min heap, so I'll go ahead and put in 2 at the top. That's the root. I have to put in values in its 2 children that are both larger than it. In other words, again, the key is the parent is less than both of its children. So we'll just say, I don't know, 10 and 50. All right. You know what? I want to go. Let's go 5 on this one. All right. Already, is that a binary search tree? No, definitely not. Everything over here needs to be less, and everything over here needs to be greater. That fits the bill, but that does not. Right? I'll go ahead and add some more children here. If I do, I need to make sure that they're both greater than their parent. 20 and 30 here. And let me go ahead and add this child here, 50. All right. Now, is that a heap? Does that satisfy all these properties? It doesn't satisfy the fullness property. What's missing? The 2 children over here. Not all nodes are present at every level except for the last level. So if I want to make this a heap, I need to make sure that both of these children are here. And I'll go ahead and put in 15. And could I put in 3? Could I put in 3 there? No, because that's less than its parent. So there's an actual heap. Let me add one more just so that I've got some additional here. 100. Okay? So some observations about this, key properties. What's our first property? The first property is, why is this called a min heap? Where's the minimum element? It's at the root. The minimum element is always at the root. So that gives us a nice property. If I've got a big pile of stuff and I've got to guarantee that the minimum is always at the top, guess what I can do? I can just go up to the root and grab that minimum, and now I've got free access, constant time access to the minimum. However, if I want to get and remove the minimum, that's going to be a problem, and we're going to talk about that in a second. But I want to look at the other property. What is the depth of a heap with n nodes? So in this particular case, how many nodes do we have here? So go ahead and count them up, and you get that there are going to be 9. Right? N is equal to 9. What is its depth? What is the depth of this tree right here? 3. So 1/3. Is that always going to be the case? Nope. Let's use some mathematics here to figure this out more generally. All right. First of all, what I'm going to do is I'm going to draw a complete binary tree over here. All right. At the first level, if I just have the root, somebody suggested that we call this a seed. If these are leaves and this is the root, and we have a tree of only one node, then what is it? A seed. That makes sense to me. I've never heard that before, but until a student pointed it out. But I'll go ahead and go with that. What's the depth here, or the depth is going to be, by convention, it's 0. And the number of nodes at that level is what? Well, there's just 1. Okay. Let's go down one more depth to a depth of 1. How many nodes are there now of this complete binary tree? 2. Total of 3, but we'll worry about the total here in a moment. Let's go one more level. And I've got a depth of 2, and there are 4. And you can kind of see that this is a geometric progression. How many are there going to be at depth 3? They're going to be 8. Dot, dot, dot. If I go down to depth k, how many nodes are there going to be? Well, if this is a geometric progression, what is this? 2 to the k. Right? So in total, and let me go ahead and rewrite this as d, right? Because that is the general depth d. There are going to be 2 to the d nodes down here at the bottom. So if this entire tree is of depth d, let's label this as depth d, then how many total nodes are there? In other words, what's the sum of I running from 0 up to d of powers of 2? So 1 plus 2 plus 4 plus 8 dot, dot, dot. This is a geometric series because you're adding up a bunch of exponentially geometrically growing values. What's a closed form solution of this? And let me say right now, this is probably something, as computer scientists, you should start committing to memory, because it also corresponds to binary. If I wrote all these out, this is the first bit, this is the second bit, right? 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, right? This is a geometric progression in binary. Right? What's the maximum value that you can express if I gave you d bits? Right? This is the answer right here. What is the answer? 2 to the d plus 1 minus 1. Right? If I gave you 3 bits, what's the maximum value that you can express? Well, 3 to the d, this might be wrong. Sorry, if I gave you d plus 1 bits, right? What's the maximum value you can express? If you summed up all bit strings of that length, though, of up to that length, this is what you would get right here. Right? And why minus 1? Well, because it starts at 0. Right? So you're off by 1. So there's our answer here, that if I considered an entire binary tree of depth n, or sorry, with n nodes, then I have that it's going to have 2 to the d plus 1 minus 1 nodes. My question was, what is d with respect to n, though? Right? My analysis over here was, what is n with respect to d? We just need to flip those around. Solve for d over here. What happens? N plus 1 on the other side. Right? I'm just taking that over to the other side. Now, how do I get rid of that 2? I take the log base 2 of it. And then, of course, I subtract off 1. Right? And I get that this is big O, or theta, whatever you want to call it. If I ignore lower order terms and I ignore constants, even additive constants here, this means that it's going to be logarithmic. Awesome. Whereas with a general binary tree, or even a generic binary search tree, I have no guarantee on the depth. With a heap, I have a guarantee on the depth, meaning that that it's only logarithmic. If I can guarantee that basic operations on a heap are proportional to the depth of that heap, then I've got a pretty good data structure, right? That rivals, say, binary search. Binary search is going to be logarithmic with respect to the number of elements in an array. If I can get some basic operations on this heap, like, say, get the minimum and remove it, or add stuff to it, like we used yesterday in Huffman coding, and if I can get those to be proportional with respect to the depth, then those are pretty efficient algorithms. Okay? So let's do that. Let's review how you might want to get the two basic operations for heaps are going to be get and remove the minimum. And again, if you want a maximum, all you need to do is flip the definition and make sure that everything is greater than both of its children, and now you've got a max heap. In practice, though, you would only implement one heap implementation, and then you would use a comparator to just flip things around. Right? There's 1, and 2 is going to be insert an element. Okay? With a more general data structure, say like an array, a list, or a binary search tree, or a binary tree by itself, we would want more generic operations. We would want the 3 basic operations: insert stuff, retrieve stuff, and remove stuff. Right? Kind of like the CRUD for data structures: create, retrieve, update, and destroy. Update, of course, is not there because once you find it, you can change it, you can take it out, and you can put it back in if you want to. Right? So the 3 basic things that you would want with any data structure: there's something that holds stuff. You want to be able to put stuff in, take stuff out, and find stuff efficiently. With a generic binary tree or binary search tree, we don't have efficient algorithms for that. We're going to rectify that. But as a stopgap solution up to that, and as a review, let's review how these operations actually work. Okay, I'm going to go ahead and copy this tree over here. Say 2, 10, 5, 15, 13. And over here it was 20 and 30 and then 50 and 100. Okay, so let's go ahead and get the minimum. Well, conveniently, that's an order 1 operation, right? So in this outline, save off the root to be returned, say we're in a method or something like that. This is going to be a constant time operation because with a tree data structure, where do you start? You have access immediately to the root. So I've saved that off and 2 is gone now. So I've removed that. There's a gap in my tree now. So I need to fix it. Right? And usually when I present this in say 156, I design the tree so that you can say, all right, well, I need to go ahead and promote, you go down the wrong path. I ask somebody, there's always somebody willing to go down the wrong path to illustrate why you shouldn't do this. You look at the local information. If you look at the local information, this is the wrong way of doing it. If you just look at the local information here, is there something that you can promote up? If you promoted 10 up, would that be a heap, a min heap anymore? Nope. So let's go ahead and promote up 5 to close that gap. And now 5 is gone. Well, if it worked for the root, maybe it works for this subtree now. Let's go ahead and promote up 13. And there are no more children to promote up, so we delete the node. Guess what happens? Is that a heap anymore? No, because it's not full anymore. All right, back to square one. I like to call those Gomer questions. Gomer pile, right? He gets things wrong. It's always best to illustrate concepts with anti-concepts, right? This is the wrong way of doing it. It leads you to the right way of doing it. So we've got a gap here. Remember, we've got to have the fullness property, but we've also got to make sure to maintain the minimum the min heap property here. Originally, with that idea that I just tried, well, I was trying to get to satisfy this property first, and then fix it so that it had this property. Let me go ahead and reverse that. Let's go ahead and make sure that the fullness property is satisfied before we worry about the heap property. Okay? What could I promote up to this gap over here to ensure that it's still full, ignoring the heap property? I can promote up the last element. The element in the last row, in the last level, all the way to the right. Yeah, 100. And now, is the fullness property satisfied? Yes. But is the heap property satisfied? Is this less than both of its children? Nope. So now let's fix that. Now I can take the idea of promoting up the minimum child, right? So save off the root to replace the root with the last key, right? Deleting its node. And then we will fix the heap. The way we'll do that is by simply exchanging it with the minimum of its two children. We'll take 5 and promote it up and push 100 down. So we ended up making this swap. Okay? Is it a heap? Is it a min heap yet? Nope, we still need to promote the minimum of these two. So we'll go ahead and promote 13 up, and 100 goes down. And so I ended up swapping these. Right? And now is the heap property satisfied? Yeah, it has no children, so it's less than both of its children, right? Vacuously true, okay? So we fix the heap. We exchange the swapped element with the minimum of its children until either the heap property is satisfied or, in this case, the heap property was satisfied vacuously by going down to a leaf, or it becomes a leaf. Okay? And this was an order 1 operation. I'll tell you right now that this is an order 1 operation if you implement your heap in a certain way. And I'll talk about how to do that here in a second. Fixing the heap, though. Starting at the top and exchanging until you get down to the end of the heap. Tell me about that. That's going to be order what? Order D, where D is the depth of the tree. Because you can, when do you stop? Well, you stop at, sometimes you might get lucky and you'll stop in the middle, or maybe you stop immediately. That's not very likely unless it's a very small heap. But sometimes you can get lucky and you can stop in the middle somewhere, right? Depending on the topology of this tree right here. But in the worst case, you end up swapping it all the way down. In other words, it's proportional to the depth. But remember, our analysis over here of the properties tells us that the depth is order log n. So this ends up being order log n. Excellent. We can get and remove the minimum element from a heap efficiently. Right? What about inserting an element? Let me go ahead and copy and paste the tree again. 5, the one that we've got now, 10, 13, 15, 100, 20, 30, and 50. There we go. Let's say that we want to insert 7. How do we go about doing that? Well, if you're familiar with a binary tree or binary search tree, generally you always start at the root and then you work your way down. But if I start at the root here, then I need to necessarily shove something down, shove something down, shove something down. Inevitably, that's going to lead to cases where you shove it down all the way to the right and you end up with this huge gap, violating the fullness property yet again. So same strategy as before. Let's satisfy the fullness property and then worry about the heap property as a second step. So step 1, where can I insert it so that I have satisfy that fullness property? Where? As the next last element, right? So insert at the end of the heap. And by end, we mean at the very last level, all the next available leftmost spot. And if you don't have one of those, then you start a new level, okay? And that's why I'm putting an end here. If I say last and end, it'll become abundantly clear why I'm using that terminology when we talk about how to actually implement these things. So I've inserted it as the last at the end of the heap. Now I need to fix the heap. Sometimes you call this heapify. All right? So I need to fix this by promoting it up with its parent if it's out of order. Right? This violates the heap property. So I'll move 20 down and I'll promote 7 up. Right? Does this satisfy the heap property? Nope, because it is not less than its parent, or its parent is greater than it, so we need to continue. I will swap this again. And we've got 10 down here and 7 over here. Do I need to go one more step? Well, I do need to make a comparison. 7 is less than 5, so now the heap property is fixed. They're satisfied, the heap has been heapified, it's been fixed. Right? So again, this is going to be order 1 if you do it properly. And this is going to be order D, which is order log n, because of that fullness property that gives this to us. Right? So how do you go about actually implementing this? Somebody asked on Piazza, everybody else is using Python, so I'll just repeat it here, that can we use a heap library? Absolutely. For Huffman coding, I said that you could use a heap. Absolutely, you can use a heap, a pre-built heap data structure. But if you're using Python, there's no need for a library at all because it's built into the language. I think it's HeapQ or QHeap. What is it called? HeapQ. Thank you. HeapQ. If you has anybody dove into the documentation for that yet, or is anybody already familiar with HeapQ from Python? What is it? It's actually not a data structure at all. All it is it's a collection of methods. Heapify. Here, what are you going to be heapifying? You're heapifying an array. Right? So, how do you represent this tree as a heap array? What I'm going to do is I'm going to go ahead and write all these numbers in the following order. I'm going to start at the top and read left to right and then go the top to bottom. So 5, 7, 13, 10, 30, 15, 100, 50, and can't read my own handwriting. I think that's a 20 though. There's my array. Dot, dot, dot. I've burned the first index here. That's okay. You don't have to in an actual implementation if you don't want to. And I don't think Python does. It does use the 0th index here. But this makes it a little bit easier to reason about. There is this heap stored as an array. If I'm at, say, this element right here, visually, its children are 50 and 20. How do I get to them? Well, 50 and 20 are right here. It's 8 and 9. In general, if I have a node at I, then its left child is going to be at node, or at index 2i. Its right child is going to be right next to it because of the way that I wrote this, right? I'm writing top to bottom, left to right. So if I write the left child, then the right child, it's just one position over. And it works in reverse too. If you want to go to the parent of 4, where's the parent of 4? Well, it's 7. You're jumping back here. What would you have had to do to jump over to this left child or this right child? And what do you have to do to jump back to it? Well, you just have to invert this function right here. It's going to be I divided by 2. Now you've got to be careful. 4 divided by 2, well, that gives me 2, and that works. But what about 30? What's its parent? 5 divided by 2, do you see a 2.5 index up here? Nope. So what do you have to do? Take the floor. Right? And this is an awesome way to implement a heap. Because now it doesn't even involve a bunch of nodes, go to the left child, go to the right child, whatever. It's just a straight old array. And that's how Python does it. Python doesn't actually have a heap. It just forces you to use an array. You can give a generic array to heapify. It'll do the fixed process, right? It'll create an ordering of these elements that satisfies a heap property. And by the way, you can do that generically if you want to, just by sorting it in ascending order, right? If we had 5, 7, 10, 13, 15, ... If we sorted this in ascending order, that would give us a heap. But of course, if we start doing operations on it, adding stuff, removing stuff, then it could be just start getting jumbled up, and we still have the heap properties, but it's no longer sorted. Right? That's how Python works. It heapifies it, it fixes it so that a heap property is satisfied, and then you call these methods on it that insert an element, and then it heapifies it again. Give me the minimum element, and it heapifies it again. Right? So there's actually no heap data structure in Python that I know of. It's just it just has you use an array. Right? So that's a review of heaps. Right? Applications, of course, would be heap sort, right? An efficient sorting algorithm, an efficient way of implementing a priority queue. Because the next one out is the one with the highest priority. You can insert stuff, and where it ends up, who cares? Because the priority dictates the way stuff comes out. And a couple of other things that you can do. And of course, an application that you're going to code would be Huffman coding. Right? Okay. Now let's go ahead and review binary search trees. I touched on this very briefly yesterday. But binary search trees are binary trees, of course, it's in the name, meaning that each node has at most 2 children, such that every node's key, k, is such that every node in K's left subtree is less than K, and every node in K's right subtree is strictly greater than K. You might be asking yourself, well, what about duplicates? What if I have a binary search tree full of 10s? You can do that if you really want to. Most programming languages, though, prefer that you break ties somehow, or that you don't allow duplicates or something like that. And it's just a technicality. Don't worry about it. You could also have a binary search tree implementation that was just simply consistent, that this is less than or equal to K, and then you know that you always need to go left. Or that this is greater than or equal to K, but you certainly can't put equals on both of these things. All right, so again, visually, what it looks like is there's a key K, and everything over here in this left subtree is less than K. Everything over here in this right subtree is greater than K. And that enables you to do basic search, insert, insertion, retrieval, and deletion. Okay? Let's go ahead and go with retrieval here. As an example, let me go ahead and write a binary search tree. 50, 100. What could I put as a left child of 100? Could I put 25? It's less than 100. Could I do that? No, why? It's inductive. Everything over here in this right subtree has to be greater than 50. So I could put 75 instead. I could put 150 over here. What could I put here as a right child of 75? 85. Okay. And let's just go with 1 over here, 10, and then 5 and 15. The way that I wrote this, I intentionally made it kind of sparse. Not all the children are there because in a binary search tree, you don't have that fullness property. And consequently, you don't have any guarantees on the depth. Okay? Here's another binary search tree. 50, 60, 70, 80, 90, ... Say that there's no node has any left child, right? So what's the if I said that there were n nodes here in this degenerate skewed tree, what's its depth for this particular tree? N minus 1, right? Is that really a tree? I mean, it is. It's a binary search tree, but it's degenerate. What is it really? It's just a linked list. All right? So we're going to solve that problem by the end of certainly tomorrow. Right? But let's remind ourselves of those 3 basic operations. How do we insert stuff? How do we retrieve stuff? How do we delete stuff? So what about retrieval? Let's say that we want to search for 10. Okay? We start at the root. Okay? All I have is local information here. 50. So that's not what I'm looking for, so I need to continue traversing the tree. Which way should I go? Remember, it's a binary search tree. Everything to the left is less than 50. Everything to the right is greater than 50. So if I'm searching for 10, which direction should I go in? In the left, right? 25. Well, 10 is less than 25, so I go left again, and I find it, right? You traverse left or right until you find it, a match. Or what's another stopping condition? So if I come in here and I search around and say that I'm searching for, I don't know, 42. Would I end up finding it? I would come in 50, that's not 42, go left. 25, that's not 2, go right. And I've fallen off the edge of the tree. So I would result in an unsuccessful search here. I would output no such element or whatever you want, right? Until you find a match or you reach the end of the tree. Okay? Well, both starting at the root, yeah, that's clear. Going left, right until you get to where you need to be, or you get to the end of the tree. This is clearly going to be order D. But I cannot write that this is order log n because I do not have any guarantees on the depth of this tree. Right? So it could be that it's order n in a degenerate case. Okay? That's retrieval. What about insertion? I didn't find 42. What should I want to insert it now. So insert 42. So I would say, well, 50, it's less, so it needs to be in the left subtree. 25, it's greater than it, so it needs to be in the right subtree. Hey, you know what? There's free real estate here. Right? Let's go ahead and put in 42 because it's vacant. It's a vacant lot, right? So in other words, you're just doing a search and you're inserting as a new leaf. That's it. Also, order D, because this insertion process of creating a new node and making the parent point to it and it back to the parent, that's just a bunch of pointers or reference shuffles. So searching order D, that's going to be the real work there. What about deleting? So let me go ahead and copy this again. 50, 25. And I won't include that one that I just inserted. 5 and 15, 100, 75, 150, and 85. So help me out. Delete, say, 85. Well, what's the first step? Find it. Right? In other words, you're doing a search, which is going to be order D. Okay. 85, there it is. What do I do to delete it? Just make its parent not point to it. Make it not point to the parent if you really want to. And if you're in a programming language that requires manual memory cleanup, then you would free up this node. Otherwise, Java, Python, PHP, et cetera, you wouldn't worry about it. You'd let the garbage collector take care of it for you. Right? Okay. That worked because it's a leaf. Right? So if it is a leaf, simply just delete it. We don't have to worry about the larger topology of the tree, because do you have to worry about a tree falling down if you go up and snip one leaf off? No. If you go and you start cutting cutting a branch, though, all the branches that come off of that branch, those are going to be cut with it. You don't want that to happen. You just want to cut off that one thing, that one bud or whatever you want to call it. Right? You didn't know that computer scientists were supposed to be arborists, did you? Right? Or there's another word for tree people. Not arborists, but the people who actually take care of the tree. I don't know. Arborists, there's some other word. I looked it up one time. But anyway, if it has one child, then for example, 25. How do we delete 25? Well, again, we search for it and we find it in order D. But we can't just delete it, because if we deleted that, what would happen to this left subtree? That entire branch would fall. And we don't want to lose that data. So if it has one child, what would you end up doing? Well, if it has one child, it kind of looks like this linked list, remember? And how do you delete from a linked list? By simply just circumventing it with the pointers or the references. So we promote the single child. The way that we would, again, visually that we would do that is we simply just take 50's left child is now 10, and 10's parent is now 50. You've circumvented this, and again, programming language that doesn't require manual memory management, it would go away automatically. Otherwise, you would probably want to clean this up, free it, if it were C. Okay. So far, so good. What if it has 2 children? And here's an example, 50. Say we want to delete the root. Well, if I deleted the root here, I could promote this left subtree, or I could promote this right subtree. How would that work? I mean, I can't promote this right subtree because 75 is the left child of 100, and 25 would need to be the new right child. In this particular example, I could promote this up and it would still work, but what if I had 42, the thing I just inserted? Now, one of these gets promoted up and they end up having 3 children. You can't do that, not in a regular binary search tree. Right? So what do I do instead? I delete it and clear it out like I did for a heap. Right? What could I put there instead? I could put 100 up there, but then I would have I would just be shifting the problem down here, and which one do you promote? 75, I could promote that up. So I could do some heapification process if you really wanted to. I'm sure that I could come up with a Gomer counter example to that, though, where that would not work. So what could I just take anything else in the tree and put it up here and have the binary search tree property satisfied. I could do what? I could do 85. All right, let's go with 85 up here. Is that a binary search tree? Careful, what about 75? 75 is less, but it's in the right subtree. All right. Not 85. Close though. I could do. Which is the one that gave me trouble? I could put 75 up there. But wait, you've just shifted the burden. How do you delete 75? Oh, it has one child. Promote that child up. Why did that work? What's an alternative? Other than 75, there's one more that I could have done instead. 42. I could promote 42 up here. It has no children. I know how to delete that. It's a leaf. Delete it. Right? 75, I could do that, and it has one child. I could delete it. Right? So what's so special about 42? It's the maximum of the left subtree. So replace the root, not just the root, but replace the node with the maximum value in the left subtree. Or 75, tell me about 75. What's so special about 75 here? It's the minimum value in the right subtree. In the right subtree. Great. The only possible problem is what happens if the maximum or the minimum, what if it has two children? If it has, like we said, 42, no children, I know how to delete that. Is 75, only one child, I know how to delete that. What if I've got the maximum and, it came down from here, whatever, and I've got two children, A and B. How do I take care of that situation? And then stuff hanging off of them if you really want to. How do I take care of that situation? Do I need to promote it though? Remember, I'm claiming that this is the maximum. Tell me about B and the binary search tree property. It should be bigger, so that's not the maximum. That's even larger. So the maximum will not have a right child. The minimum will not have a left child. This is impossible. It's either going to be the case where it's a leaf or it has one child, and in either one of those cases, you know how to delete it. Right? So not possible. Proof by contradiction, even though we didn't write it out as a bunch of propositions and implications and stuff. Right? A proof by contradiction, suppose that the maximum has a right child. Right? Well then, the right child, label it B, existential instantiation. B, by the binary search tree property, B is greater than max, therefore contradiction. The maximum value is not the maximum. Right? Okay. That's those three basic operations. You need to be able to insert stuff, retrieve stuff, and delete stuff. But the problem with binary search trees, binary search trees may not be balanced. Right? In other words, their depth could be order n. And since all three of those operations were proportional to the depth, I'm not buying myself anything by creating a binary search tree over, say, a linked list. Right? What we want, our goal, will be to add more structure to BSTs to guarantee that the depth will be order log n. And if you've got that, all three of those operations are going to be efficient. Okay? This gives us what are called balanced binary search trees, BSTs. And I don't know where my list is, but there are at least a dozen different implementation or different variations on these. Let's see. Well, I'll just start listing them. There are AVL trees. There are B trees. There are, and then a variant of which 2-3 trees that we're going to look at. We're also going to look at AVL trees. You've got red, black trees. You've got, I think, Heaps. Where's my full list? If you just look up like balanced binary search trees on Wikipedia or something, you'll get an entire list of possibilities. I don't have a list here, oh well. From memory, I think Heaps maybe, right? And et cetera, et cetera, et cetera. We're going to focus on 2 implementations here to show you some basic ideas and approaches on how you can achieve this balance. Right? We're going to, and it's generally achieved by either adding additional structure or additional operations, such that when you insert something or you delete something and a tree becomes unbalanced, you rebalance it somehow. Okay? And the first version that we're going to look at are AVL trees because they achieve a balance exactly that way. Right? So let's go ahead and assume that we have, say, A is less than B is less than C. We've got these 3 keys. Okay? Here's a potential unbalance, A, B, and C. Right? There's a binary search tree, but it's unbalanced, right? What's a better representation of this? What is a balance? It's unbalanced because everything is skewing to the right. There's nothing on the left. So could I say rewrite it and could I do this? Could I say, all right, I'll move C over here. C, A, B. Remember, I put the conditions here that A, B, and C are less than, less than. Can I do it like this? Nope. So what do I need to do? I need to rebalance it. Imagine that there's this hill here, right? And that this is a chain and that you're at the top of the hill. Pull the chain to the other side of the hill, right? And what does that result in? B comes at the top of the hill, C is still over on the other side of the hill, and A, you've pulled that down to the other side of the hill, and now it's rebalanced. This is a rotation. It's a left rotation because we're rotating it left about this imaginary hill, okay? And it's rebalanced, okay? Well, you might imagine the reverse situation. Well, what does it look like if it's skewed to the other side? What if I've got C, B, A? Well, again, draw your imaginary hill here and rotate it. What kind of a rotation would you call that? A right rotation. All right? And what does it look like eventually? B, A, C. Are those the only 2 possibilities? I've got A, B, C here. Draw me any old trees. You know what? Let's get some practice here. And I'm going to replace A, B, and C with 10, 20, and 30. Let's insert these in various orders into a binary search tree. If I insert 10, then I insert 20, it becomes the right. And then I insert 30, then I get this tree. We've already seen this tree. This is unbalanced and you'd have to do a left rotation. What's another possibility? How many permutations are there of 3 things? Permutations of 3 things are going to be 3 factorial, 6. So there's one permutation. Here's another permutation, 30, 20, 10. So if I insert it in this order, 30 gets inserted, then 20, then 10. All right? I need 2 more permutations here. Give me another permutation. 10, 30, 20. I insert 10, I insert 30, and guess what? I insert 20. Just by inserting it in that order, I've got a balanced tree already. Right? So this is unbalanced, unbalanced, this is balanced. Here's another permutation. 20, 10, and 30. What is that going to look like? Oh, you know what? Sorry, rewind. 10, then 20, where's, sorry. 10, 30, where does 20 go? 20 is greater than 10, it's less than 30, so it gets inserted here. All right? That's skewed to the right. Now, what is, this is the one I was thinking of. 20, then 10, then 30, that results in a balanced binary search tree. Here's another permutation, 20, 30, and 10. Well, you end up going with 20, then 30, then 10, also balanced. Give me the last permutation. 30, 10, and 20. If I insert 30, and then I insert 10, and then 20 gets inserted over here, this is unbalanced. Unbalanced, this is a left rotation. Unbalanced, this is a right rotation. Unbalanced and unbalanced, balanced and balanced, we don't have to deal with that. What do we do if it's unbalanced in a zigzaggy fashion? Right? Ultimately, I want it to look like these balanced trees over here. Right? So let's go ahead and focus on this first one right here. 10, 30, and 20. It's unbalanced in a zigzaggy fashion. It's unbalanced to the right, and then the right subtree is unbalanced to the left. So what do? We do two rotations. We do a right rotation, giving us, this is just an intermediary here, giving us 20 and then 30. You see what I did there? I went down to the bottom of the tree, I had this imaginary hill, and I moved it over here. And now this is unbalanced to the left, so I do a left rotation, and I end up with a balanced binary search tree of 10, 20, and 30. Pretty cool. This is a right, left rotation. The other one is just a mirror of it. So if I had 30, 20, and 10, then it's unbalanced to the left, and its subtree is unbalanced to the right. So I need to go in reverse. I do a left rotation, and then a right rotation. Right? And I end up with the same one up here. This is a left, left, right rotation. And you can go with LR or RL for short. Sorry, was it? 30, yes, 30, 10, 20. Because that's not a binary search tree. Thank you. There we go. That's why I switched over to a pencil. Okay. It's not as, I don't know what it looks like. It's okay, but it's not great. All right. Okay. So those are the types of rotations that we can do in an AVL tree. By the way, AVL doesn't stand for anything other than the inventor's names. I don't know what, I don't even remember what they are off the top of my head. I could look that up, but it doesn't really matter. Right? Forever, they will be called AVL trees. Oh, there it is. Adelson, Velsky, and Landis. Right? So there's no, they're just named after the people that came up with them. I don't know if they named it after themselves, or generally when they go into common usage, they'll just credit the original authors by naming it after them. Right? Well, you can see this visually, right? Because you're a human. You can see that it's skewed to the right and that it's skewed to the left, and that, well, now I need to do a right-left rotation. You can see that because it's written down on a piece of paper, and we're smart humans. Think about a dumb computer. A dumb computer, if I just gave it a tree, what do you mean it's unbalanced? It's just a bunch of bits in the ether, right? It's just a bunch of electronic signals. What do you mean that it's unbalanced or balanced, right? So we need a way to quantify that. We need a way to define a balance factor that can be maintained and updated. So, definition, and I think I reviewed this yesterday, but it serves to define it again. The height of a node U in a binary tree is the length of the longest path from U to any descendant leaves or leaf. Right? Now, just as a callback here, remember the longest path problem? You did this in quiz 1. What is that kind of equivalent to? If I had an answer to the longest path problem, if I had a graph and I asked this oracle, right? An oracle is an all-knowing thing that you can ask questions of, right? Here's a graph. What's the length of the longest path? And they said, oh, it's 5. And my graph had 50 vertices. Would I have an answer to the Hamiltonian path problem? Yeah, that's not long enough to be a Hamiltonian path. A Hamiltonian path in a graph of 50 vertices is going to be of length 49. Right? So if I had that oracle telling me answers to what's the longest path question, I'd be able to solve the Hamiltonian path problem, which is an extremely difficult problem. This is a difficult, and thus the longest path problem that the oracle is answering for me, that's also an extremely difficult problem. But as a callback, remember, this is a tree. Is it an extremely difficult problem? If I ask that same oracle, here's a tree, what's the length of the longest path from this node to this node? What would the answer be? Let me rephrase the question. How many paths are there from this node to this node in a tree? Exactly 1. So if you find it, then that's the longest one, right? There's no guesswork there because we have a lot of structure, right? So that is just a callback to something that we've covered and that we will revisit again. So the length of the longest path to any descendant leaf. Let me go ahead and draw a tree, and we'll go ahead and start talking about balance factors and heights here. 40. I'm just copying this tree that I've got in my notes. I don't know. If you have text and you went to the trouble of actually drawing stuff in Tixie, I think that they're more than notes. But, oh well. So let's just go ahead and take a subsample here. What are the heights? Here's the node. Say 10, and its height. So what's the height of 10? It's the length of the longest path to any one of its leaves. The leaves here are 4, 7, 30, and 50. So the length, clearly this is going to be the longest one because of the way I drew it. So 1, 2, 3, 4. What about 30? What's its height? 0, right? So leaves, the height is 0. Another example, what about 40? 1, 2. What about 80? 80 and 30 are on the same level, but do they have the same height? Nope. So leveling does not have any bearing on the height of a node. Okay? Remember, those are heights. Definition. The height of a tree is the maximum height of any of its nodes. Let me rephrase this. The height of a tree is the max of any of its nodes. Well, what's going to be the max? I.e., the height of the root. That's where the height is going to be maximized, right? Because it's already defined in terms of the longest path. In this case, this tree, the tree's height, tree height, is going to be, we've already enumerated it here, 4. Okay? You can also talk about subtrees. If I look at the subtree 6, or we've already done it here. What's the let's go with 40. If I chopped all this off and treated 40 as its own tree, what's the height of that tree? It's 2. Okay? So let me reuse this over here and just do definitions. So another definition. The balance factor, BF, of a tree, or let's rewrite that as a node, is defined as, of a node U, BF of U is equal to the height of T sub L minus the height of T sub R, where TL and TR are the left and right subtrees of U. So some corner cases here that we have to take care of. Remember that I said that a single node tree is our seed, right? So if a single node tree has height, what did we say? If I go back over here and I look at 30 in isolation, what's the height of that subtree? It's the height of the root, which is 0. But what about an empty tree? An empty tree has height by convention. What would make sense? Could I give it a height of 10? Well, it's empty. It's got no height. Well, could I give it a height of 0 if it has no height? Well, that's already reserved for the single node case. So working in the other direction, -1. Right? That's the convention to make the math work out. Okay? So what I'm going to do is I'm going to go ahead and go back to this example here. Now let's go ahead and start it on a new page. So 10, 8, 40, 6, 7, 30, 80, 5, and 4, and then we've got 50 over here. Okay? Let's look at a subsampling of these nodes here. What about node 10? What is its balance factor? Remember that the balance factor is the height of its left subtree minus the height of its right subtree. So its left subtree is over here. Tell me about the height here. What's the height? 1, 2, 3. Minus, what's the height of this tree over here? 2. So it's 1. Okay? What about the height of node, say, I don't know, 8? Let's look at the left subtree here. What's its height? 2. What's the height of this tree over here? Did I just screw up already? Say what? Oh, sorry. What? No, wait. 8. Okay. No, its left subtree is going to be 2, right? Yeah, node 8's left subtree is this thing right here, right? And what's its height? 2, okay? Node 8, its right subtree, its height is, 0, okay, yeah, there we go, 0. So minus 0, which is equal to 2. Oh. Actually, no, I just copied it wrong and I just made it bigger. You're right. I'll fix it by going 9. I don't want to change the topology. Thank you. Oh, and no, this is correct. What about 9, though? What's its balance factor? Well, 9's left subtree, guess what? It's empty. What was the height of an empty tree? negative 1 minus the right subtree is also empty. What's the height of a negative of an empty tree? Negative 1. Be careful. Don't just say 1 and then get the wrong answer. Minus 1, negative 1 minus negative 1 is going to be 0. Good. Let's look at another example here. 6. 6's left subtree is just 5 and 4, so its height is 1. But 6's right subtree is empty. It has a height of negative 1. So when I subtract that off, what do I get? I get actually 2. Right? Select any one. Fast forward here. Based on what you saw with 9 being 0, all leaves will have a balance factor of 0. So 0, 0. Let's go ahead and go with 30, 50, 4. And these are all going to be 0, 0, and 0. We still have to do 5, 80, and 40. Tell me about 5. Its left subtree has a single node, which has a height of 0. Its right subtree is empty, so negative 1. And we've got that it's going to be 1. Okay? 80 is going to have a right subtree is 0. Well, that's the exact same thing as 5 over here, minus negative 1, so 1. And what about 40? Its left subtree is a single node, so 0, minus its right subtree has a height of 1, so minus 1. Right? So already we see 0s and 1s and 2s, and we can have negative 2s. Those are okay, right? This is kind of a balanced tree overall, right? But it's when we start to get very, very skewed trees that we need to start taking action and starting to rotate things around. Let's go back. Now that we have an understanding of a quantification for whether or not something is skewed to the left, to the right, whatever, let's go back to our examples. What if I have 30, 20, and 10? Right? The one where I did a right rotation. What are the balance factors here? Well, what's the balance factor of 10? Negative 1 minus negative 1 cancels out, and we've got a balance factor of 0. What about 20? Balance factor of 0 minus negative 1, that's going to be 1. Balance factor of 30, 1 minus negative 1 is going to be what? 2. 2 is too much, right? Now, that other example I said that's not too bad. We're not going to tolerate it, though. We're going to tolerate 0, which is perfectly balanced, right? Now that Marvel's out, we can use that as a meme, right? You want to make it so that it's perfectly balanced, right? You want to Thanos it. Yeah, there. I'm going to call it Thanosing it from now on, right? But 1 is okay. It's slightly unbalanced, but 2 is not. Another example. What about 10, 20, and 30? There's a binary search tree that's skewed to the right. Again, balance factor of 0 because negative 1 minus negative 1 cancels out. Negative 1 minus 0 is negative 1. Negative 1 minus 1 is going to be negative 2. Just the mirror image of that. The mirror image, and then what happens to all the signs? They get negated. Right? So, a balance factor that is negative, or as I say positive first, indicates it's skewed to the which direction? Left. And if it's negative, it is skewed to the right. Consequently, if it's skewed to the left, what kind of rotation do I do? To rebalance it? A right rotation. If it's skewed to the right, what kind of rebalancing do I need to do? A left rotation. Okay? What about those two others? Let's say 30, 10, and 20. It's zigzaggy skewed. Let's go ahead and write down the balance factors for these. What's the balance factor of this? -1 minus -1 cancels out, 0. -1 minus 0 gives me -1. And 1 minus -1 is going to give me 2. A positive balance factor indicates that it's skewed to the left, but then a negative balance factor indicates that it's skewed to the right. So a left-right rotation occurs when you've got this situation. 2, and then it's left child. That tells you it's skewed to the left, so you look at the left child's balance factor, it tells you that it's negative, so you need to skew it, it's skewed to the right. Likewise, if we've got 10, 30, and 20. What are the balance factors here? Again, 0, -1 minus -1. 0 minus -1 is going to be 1. And -1 minus 1 is going to be -2. Again, it is just the mirror image of this, and all of the signs get negated. Right? So keep that in mind. You're going to be writing the pseudocode to actually do this. I'm giving you a little bit of a start here, but you're going to write a pseudocode that, given the balance factors of all these nodes, you have to determine, well, do I do a left rotation, a right rotation, left-right rotation, right-left rotation, or, hey, it's balanced, don't do anything. Right? All right. Let's look at what these look like generally. In fact, I don't like, yeah, okay, we'll go ahead and draw it like this. Here's a general left rotation. These examples were with particular keys and only 3 nodes in the tree. What would it look like if you had these big giant trees hanging off of everything? So let me go ahead and write R and C. And let's say that we have an unbalancing factor here of -1 and 1. But also we've got these big giant trees hanging off of them, T1, and say that it has both children. I'll call it T2 and T3. Now remind me, or we can go back to the last one here, what does this look like? What kind of a rotation should I do here? This is -2, it's unbalanced. Which direction is it unbalanced in? It's skewed to the right. You look at the right child, it's negative, so it's skewed to the right. So what kind of rotation should we do? A left rotation. And when we do that, we do it about R. Right? So again, imagine that there's this hill right in between, and you're pulling it over because it's all linked together. C comes up to be the new root. What happens to all these trees, though? Right, R is now over here because you pulled it across this hill right here. T1, T2, T3, we still have to account for those. Where are they? Let's reason about this. T3, everything in here is greater than C. And by transitivity, it's also greater than R. Right? So where could I put it over here? It has to be greater than R, so maybe it could be over here. But that would be, R is now a left child of C. Can it go over here? Nope. The only place that it can go is over here as still remaining the right child of C. Likewise, if I look at T1, everything in here is less than R, and by transitivity, it's less than C because C is greater than R. And so the only place that it can go is over here, T1. That leaves us T2. And by process of elimination, there's only one spot where we can go. Where? As the right child of R. So what happened here? T2, which was the left child of C, swings over, right? This swings over to become the new right child of R. Right? And that's what you have to do if you've got additional trees hanging off of this stuff. That wasn't a concern over here with our simple examples because there was nothing hanging off of these things to worry about. But in general, you do have to worry about this general situation. By the way, what does a general right rotation look like? That you've got C and R and it's 2 and 1. So go ahead and pull it up over here. It's just the mirror image, right? That T1 and T2 now swings over to become R's left child. Right? And I didn't want to waste my time drawing it again. Just besides, look at those drawings. They're so nice, right? They're way better than anything I could do on here. Right? It take a long time too to draw them nicely like that. Let's look at a generalized, say, LR rotation. What that's going to look like is skewed to the left, LR, yeah, and then here's C, and here's G. And by the way, there's no rhyme or reason to G, C, and R. They're just names. I chose them here because root, child, G. If this is the father, this is the son, what is this? Grandson, so G. Right? That's the only reason I chose it like that. Say that we've got T1 hanging off of here, T2 hanging off of G, and T3 hanging off of G. And suppose that we've got another big giant tree over here, T4. Now, this is a generalized LR rotation, so we have 2 positive indicates that it's skewed to the left. Right? Negative indicates that then it's skewed to the right. So we need to do a left, then a right rotation. Let's do that in 2 steps. If I do a left rotation about this, what does it look like? R, then the grandchild has now become the child, right? And we've got C over here. Where are all these trees hanging off of? T4, right? C still has T1 hanging off of it. What happened to G's trees? There's 2, and well, you could still have T3 hanging off of this, but temporarily, this is now an orphan. Right? If you're actually going to program this, and I've never, many years ago, I asked people to program an AVL tree in, say, Java or something like that, just as an exercise. It's never good. It's never turned out well. There's always like these special cases and everything. I do ask you to write pseudocode, but I don't ask people to actually implement these things anymore. But because you have so much juggling to do. So this is going to be a temporary orphan after the left rotation. Now what we're going to do is we're going to do a right rotation. And when we do that, G becomes the new root. R is its left child, and C is over here as its left child. Now T2 can find a new home. And by the way, in this, T3 then becomes an orphan too temporarily. So T1 is still hanging out as the left child of C. T4 is still hanging out at the right child of R. But now these 2 things are orphaned. Guess what? There's new free real estate here where they can go. T3 and 3 and 2. Now, just to make sure that we were correct on this, let's go ahead and infer the relationships here. What do we know about all of these relationships? First of all, we know that everything, this isn't proper notation, but we know that everything in T4 is less than, or is greater than R. Is that still satisfied here? Yep. What about T3? We know that everything in there is greater than is greater than G. Is that still satisfied? Well, it's over here, the right subtree of G. That looks good. We know that everything in T2 is less than G. Well, is that still satisfied over here? T2 is in G's left subtree, so that's good. Okay. So good, good, good. What about T1? T1 is less than C, and it never changed anyway, so that's still good. What about the relationships between R, C, and G? Originally, what did we have? That G is greater than C, because it's a right child, and they're both less than R. Does that still hold over here? C is less than G, so it's a left child. R is greater than G, so that's it's a right child, and everything checks out. Right? And again, I don't want to beleaguer this with drawing everything else and drawing it all again, but in as a mirror image. So there you go. That's what it looks like. You've got all these things hanging off of here. When you do the right rotation, this one gets orphaned temporarily. Then you do the left rotation, this one gets orphaned temporarily, and you have to reconnect them to R and C. Okay? And that was our AVL trees. How do you do the basic operations? Right? So search is exactly the same. What about insertion? Same. You insert as a leaf. But in addition, you rebalance if necessary. And the great thing about this is that if you have to rebalance at a node, that's only local, right? You only have to rebalance this subtree because it's skewed this way or it's skewed this way. The balance factor everywhere else, once you fix it, it's unchanged over here. Right? And you don't have to, you only have to rebalance it, I believe, once. Okay? So it's, the rebalancing, by the way, is order what? You do have to update the balance factors going up. So that's order, say, log n at most. But ultimately, if you've got 2, 1, or 2, negative 1, or negative 2, negative 1, negative, or positive 2, positive 1, you're only doing local information here. All I mean, visually, I'm rotating these things, but when you're actually programming them, all you're doing is shuffling around a bunch of references, right? T's parent becomes from G. You set that T2's parent becomes, you reset it to C. T's 3 parent, you reset that to R. So it's just like 4 or 5 lines of resetting stuff. Okay? That's all constant. Uh-oh. What about deletion? How does that work? So for this, I'm going to appeal, since we're running out of time here, I'm going to appeal to the very nice, if I do say so myself, very, very nice figure that I drew at some point because I've never seen a book that actually gave the full AVL tree deletion visualization, basically. Oh no, where is it? I don't want to redraw it. I'm definitely not going to be able to redraw it from memory. I swear I printed it out. If not, I'll just bring it next time and we can take a look at it. But suffice to say, the issue is that deleting something could unbalance the tree above it. Ah, here we go. Good. Okay. So let me cover and cover and zoom. Ah, nah. Okay. Don't hold down zoom. That's good enough. Focus. Oh, nice. All right. Okay. So suppose that we delete the node 3, right? That means that what was balanced before becomes unbalanced. Tell me about those balance factors right there. What are those balance factors? So -1 minus 1, that's going to be, well, it's right there, -2, right? And then the balance, I don't know why I've got 0 there. I think that's what it was before. Well, let's suppose that it was 0 before. But what kind of a rotation are you going to want to do here after you've deleted 3? You're going to want to do a left rotation, right? And that fixes this balance factor right here, because now it's 12, 10 on the left child and 14 on the other side. But that screws up the balance factor of its parent, right? Look at the balance factor here. That's going to be 1 minus 1, 2, 3. So 1 minus 3 is going to be -2, giving us this balance factor. It's unbalanced. So what do I have? You didn't yell at me. There we go. Sorry. All right, there's the balance factor is 1 minus 1, 2, 3. So it's going to be -2, and we screwed up the balance, right? So we need to go ahead and rebalance again with a left rotation. That'll fix this balance factor, but guess what it does to 50? There we go. That makes it into a -2 and -1. So I believe that we have to do another rotation. What kind of rotation? It's going to be, oh, it's a left rotation again. And what happens to 60? It comes up here. T2 swings over to become the new right child of 50, and T1 remains over here. At which point we're done. Because if you fix the balance factor all the way up to the root, well, that's where you stop. So you're doing a bunch of potentially, you're way down here at the bottom of the tree, you're rebalancing, you have to work all the way back up to the top of the tree. Is that going to be a problem? No, because what's the depth of the tree? We haven't gotten to that yet, but the goal of the depth of the tree, if it's balanced, it's going to be roughly log n. So all the rebalancing all the way back up to the top is also going to be order log n. Right? Next, continue with this with a full example. We'll start with an empty tree and start putting stuff in. But otherwise, ultimately what you've got here is a rebalanced tree. Okay?